Alright, now on to definitions. So acids and bases. We've used those words a lot. You recognize those words undoubtedly. But what is an acid and what's a base? What makes something acidic? What makes something basic? So in order to come up with an explanation, because scientists knew for years that there was things that were acidic and things that were basic, they did these different things. But what makes them that way? So there's three basic definitions for acids and bases. We'll talk about all three of them, and then there's just one of them really that we're going to focus on throughout the term. So the first definition of an acid base is going to be the Arrhenius definition. The Arrhenius is the simplest of all of them. What the Arrhenius definition says is that an acid is something that dissociates in water to produce H plus ions. So an acid would be something that dissolves in water, but not only does it dissolve, but it also dissociates and it produces those H plus ions. So something like HA here. HA is a generic form for an acid, so when it dissociates it produces those H plus ions. Something like sodium chloride that also dissociates in water, but it's not acidic or basic because it doesn't produce those H plus ions. And base, on the other hand, is something that dissociates in water to produce hydroxide ions. So in this case, we're talking about BOH there. So when it dissociates in water, it produces OH minus and B plus. So a trick with this, real quick, with bases especially. So the OH does not always signify that it's basic. So if you think of something like methanol, CH3OH, that is not a basic compound because when it dissociates in water, or when it dissolves in water, it stays CH3OH. So it doesn't dissociate to produce those OH minuses. That is a key ingredient for bases. So it's not, an acid isn't just something that has an H, and a base isn't just something that has an OH minus, or an OH. It has to produce those ions in the solution. Okay, so a couple issues with the Arrhenius definition, why it really hasn't stuck very well, is it's only true for bases that contain hydroxide ions. So there are bases that do not contain the OH minus but still make a solution basic. The perfect example of that would be ammonia, which we talked about as a cleaning product. Ammonia, if you look at that, there is no OH minuses in that compound. And so by the Arrhenius definition, that wouldn't appear to be a base when all actuality it is. And it's only true for reactions that take place in aqueous solutions. So in other words, what the Arrhenius definition would say then is HCl, sitting by itself, not dissolved in water, would not be acidic. Because if it's not dissociated in water, then it's not acidic, because right there, HCl alone does not have H pluses on it. Alright, so the next definition then is the Lewis acids and bases definition. So with a Lewis acid-base definition, as well as the next one that we're going to talk about, these really describe interactions. So in order to have a Lewis acid, you have to have a Lewis base. They go hand in hand. It's like oxidation reduction. You can't have oxidation without reduction. You can't have a Lewis acid without a Lewis base. So a Lewis acid accepts an electron pair. So a Lewis acid is an electron pair acceptor, and a base is an electron pair donor. So that's the way you remember them. Acids accept, bases donate. And in this case, with Lewis, we're talking about electron pairs. So lone pairs is what we're talking about. Nice thing about this one is it does work for all acids and bases. So, for example, let's take a look at NH3. So there's the ammonia. The Arrhenius definition did not describe NH3 as a base, but the Lewis definition does. So if we look at this particular problem right there, we see the lone pair on the NH3 can be donated to the BH3. So when that happens, the Lewis base, the NH3, is the electron pair donor. So it's donating to the boron, and the boron is accepting that electron pair. So that makes this guy the base and this guy the acid. And here is our final compound then. Okay, so the electron pair is donated from one to the other. The problem with the Lewis acid and base definition is really, in order to distinguish something as a Lewis acid or a Lewis base, you have to draw out the structure. You have to draw the structure, draw the lone pairs, figure out where the lone pairs are getting donated, who gets to keep them, who's accepting them. and it, it can get kind of clumsy. So it works for all acids and bases, but it's just not a very convenient way to describe acids and bases. And so that brings us to the apex of all acids and base definitions, and that's the Bronsted-Lowery definition. So this is the big one. This is the one that you're going to see the most of, because it, like the other ones, works for most acid and base reactions. It's not quite as convenient as the Lewis acid and base definition. It doesn't describe all of them, but for the most part it always works. So the the Bronsted-Lowery definition says that acids donate protons, and in this case they're donating. With the Lewis, we think about that, and it was accepting, but acids donate protons. So acids are proton donors, bases accept protons. And a proton, just so we know, a proton is an H+, because if you think about a hydrogen atom is one proton, one electron, no neutrons. And if it becomes H+, H+ means that it has lost an electron, so that just means that this electron has gone bye-bye. And what are you left with? You're left with a proton. So really an H+ ion is just a proton. So when we talk about a Bronsted acid, it's one that donates a proton, and a base is one that accepts protons. So I said before, you can't have one without the other. You cannot have a Bronsted-Lowery acid without a Bronsted-Lowery base. And that's because in order for something to accept a proton, something has to donate it. So all acids need bases in the system as well. So it has to have something to dump those H+'s on. I know your probably initial thought is, well, if there's an acid and a base in there, isn't it neutral? Not the case. They're going to be of different strengths, different properties, and that's what makes it end up being acidic or basic. So we'll talk a little more in depth about the Bronsted-Lowery definition because of kind of its power. All right, so here is a diagram that's going to show for us the Bronsted-Lowery acid and base interaction. So with this system, you can see that there is an acid and there is a base. So there's our acid and there's our base, and that's because if we take a look here, let me get my pen. HA has that H that it's going to donate to the B, so there's that H+ scooting on over, and we get BH+. So HA has donated a proton to the B. B accepted that proton, and so B becomes BH+, and HA becomes A-. So since HA donated the proton, it's an acid. Since B accepted that proton, it is a base. Now a couple new terms that you're going to see up here, and that's conjugate. So when these systems happen, a lot of the times we set up this right here. That is equilibrium. Okay? Equilibrium means not only is it happening in the forward direction, but it's also happening in the reverse direction as well, at the same rate. And so since HA is donating electrons to, or a proton to B, on this side of the reaction, BH+ is also going to donate a proton back to A- at a different rate, okay, or at a different amount. Oops. So BH+ is sorry guys, there we go. So BH+ is going to donate a proton back to A-. And when it does that, that means that BH+ is now an acid because it's donated a proton. And A- over here is accepting that proton, and that's going to make it a base. And so when that happens, then you wind up with these guys again, and the cycle just keeps happening. So on the side of the reactants, we call them the acid and the base. On the side of the products, we call them the conjugate and the conjugate. So this right here is not the acid, it's the conjugate acid. This right here is not the base, it's the conjugate base. So this is the new acid and the new base. How do you know where the conjugate is? It's on the product side. The reactants is just the straight ups, the conjugates are on the products. We'll get lots of practice with this idea right here of identifying acid and base and their conjugates is really important. Something to note here too is that the acid, whatever the acid is on the reactants, becomes the conjugate base on the other side. Whatever the base is over here becomes the conjugate acid. So acid to conjugate base, base to conjugate acid, always. All right, so here's a practice problem for us to take a look at then. This is what you're going to see a lot of in the practice problems. So HNO2, that is nitric acid, reacting with water to produce nitrite and hydronium. H3O plus, by the way, is hydronium. It's another thing you're going to see a lot of during this unit. So if we take a look here, a good way to identify these is look over at the product side. So we see NO2, and that came from right here. And so you see that it lost an H right there. Okay, that should be a hint. Then we take a look at the H3O plus. That came from water, and we see an extra proton on that guy. So that means it accepted a proton. So we can come back here to our diagram and say that, all right, so HNO2 is going to send a proton over towards water. That means since HNO2 donated a proton, it is an acid. And since water accepted that H+, it is a base in this system. Okay, so we see that proton getting donated over. Now let's come back over to this side. So remember, whatever the acid is over on this side becomes the conjugate base. So let's find HNO2 or its daughter molecule over on this side, and that would be the NO2, the nitrite. Okay, so that means on this side it is going to be the conjugate base, and H3O plus would be the conjugate acid. Another way to identify that is we can see that in order to go back from what we have here, the products, to go backwards and produce these guys again, the H3O plus is going to have to donate a proton over to the nitrite, and the nitrite's going to have to accept that. And so since this guy is donating, it's the acid, but it's not just the acid, it's the conjugate acid. And I'm just going to write C acid. That means conjugate acid, and this would be the conjugate base. All right, pretty straightforward. Just follow the protons and you should figure out what's going down. And on this bottom one, we see it NH3, so that's ammonia. Remember how we talked about the Arrhenius definition doesn't describe ammonia as a base? Here's why it is a base. And so if we take a look here, water is going to have to donate a proton over to NH3 in order to produce the NH4+. And H2O is going to have to get rid of that one, and that's going to make it OH-. So this guy then would be the base because it accepted the proton. This guy would be the acid because it donated it. And then in order to go backwards, so those guys react to form this side, the NH4 is going to have to donate a proton over to OH-, which is going to make water and ammonia again. And so this guy would be our conjugate acid, and this guy would be our conjugate base. Okay. Something I want you guys to note here then, as you might have noticed already, on the top case, water was acting as a base, and in the bottom one, water was acting as an acid. So this is why a lot of the acidic systems take place in water, and it's because you need something to donate or accept the protons in order to make the other guy an acid or a base. It's like oxidation reduction. Something has to take the electrons or send the electrons. That property of water then, that it can be both an acid and a base, is called amphoterism. So water is amphoteric. It is amphoteric because it can act as both an acid and a base, depending on what system it's in.